Hydrology is one of the earth sciences. It studies the waters of the earth, their occurrence, circulation, and distribution, their physical and chemical properties, and their relation to living things. It encompasses surface and groundwater hydrology. Engineering hydrology is an applied earth science. It uses hydrologic principles in the solution of engineering problems arising from human exploitation of the water resources of the earth. It seeks to establish relations defining the spatial, temporal, seasonal, annual, regional, or geographical variability of water. It aims to establish risks in sizing hydraulic structures and systems. The hydrologic cycle describes the continuous recirculatory transport of the waters of the earth, linking atmosphere, land, and oceans. Water evaporates from the ocean's surface and moves inland. Atmospheric conditions act to condense and precipitate water onto the land surface. The return of water to oceans is through surface runoff, driven by gravitational forces. The water-holding elements of the hydrologic cycle are atmosphere. Clouds are contained in the lower atmosphere. Vegetation. Tropical rainforests have great quantities of biomass per unit of area, and the biomass contains a lot of water. Snowpack and ice caps. Glaciers can hold great quantities of water. Land surface. Vegetation gradients reveal differences in moisture. Soil. Soil can hold significant amounts of water. Streams, lakes, and rivers. Streams flow by gravity from headwaters to ocean. Aquifers. Aquifers can hold great amounts of water. Oceans. All water originates in the ocean and returns to the ocean. The liquid transport phases of the hydrologic cycle are precipitation, from atmosphere to land surface. Throughfall, from vegetation to land surface. Melt, from snowpack to land surface. Surface runoff, from land surface to streams to ocean. Infiltration, from land surface to soil. Exfiltration, from soil to land surface. Interflow, from soil to streams. Percolation, from soil to aquifers. A catchment is a portion of the land surface that collects runoff and concentrates it at one point or outlet. The outlet is referred to as the mouth. The terms watershed and basin refer to catchments. Small catchments are watersheds. Large catchments are basins. The hydrologic budget is an accounting of the various transport phases of the hydrologic cycle. The following budget considers both surface and groundwater, where delta S is the change in storage, P is precipitation, E is evaporation, T evapotranspiration, G groundwater flow out of the catchment, and Q surface runoff out of the catchment. The following budget considers only surface water, where I is infiltration. Note that there is some double counting, because infiltration, I, can return eventually as evapotranspiration, T. Likewise, infiltration can convert to base flow and eventually return to the surface water as part of surface runoff, Q. For certain applications, where the change in storage delta S is 0, and the sum of E plus T plus I can be taken as the losses to runoff, L, then runoff is This equation is very useful in flood hydrology. There are many uses of engineering hydrology. Examples are the calculation of the probable maximum flood, the PMF, at a dam site. All dams require some type of spillway. The variation of water yield from season to season and from year to year. Most of the water in deserts goes to evaporation, while most of the water in rainforests goes to runoff. The relation between surface water and groundwater. The quantities of groundwater are about 100 times greater than the quantities of surface water. The permanence of low flows to provide for economically beneficial uses such as hydropower, inland navigation, and water quality. The multi-annual variation of flows for the purpose of sizing large storage reservoirs. Hydrologic field equipment to measure precipitation and stream flows, including hardware and software. Models are either material or formal. Material models are physical representations of the prototype, that is, physical models. Formal models are a mathematical abstraction of an idealized situation. Material models are either iconic or analog. Iconic models are simplified representations of real systems, such as the lysimeters of Coshocton, Ohio, and San Dimas, California, and the USDA Agricultural Research Service Walnut Gulch Experimental Watershed near Tombstone, Arizona. Analog models use other substances, such as electricity. All formal models are mathematical in nature. Mathematical models classify into deterministic, which are formulated using physical or chemical laws; probabilistic, which are governed by laws of chance; conceptual, which are simplified representations of physical processes intended to work in the mean; parametric, which use algebraic equations and are limited to a certain region. The kinematic wave routing is deterministic. The Gumbel method of flood frequency is probabilistic. The cascade of linear reservoirs is conceptual. The runoff curve number is conceptual, but based on parametric data. The USGS state equations for flood peak estimation are parametric. The rational method is conceptual because the peak flow Q sub P follows the principle of runoff concentration, that is, the product of rainfall intensity times the drainage area, and parametric because the runoff coefficient is empirical. Hydrologic models can be lumped, distributed, or quasi-distributed. The lump models describe temporal variations but cannot describe spatial variations. The distributed models can describe both temporal and spatial variations. A quasi-distributed model such as HMS's modified Clark is a hybrid, that is, a lumped method in a distributed GIS context. The solutions can be analytical or numerical. The models used in practice are numerical in nature, such as HMS. Surface runoff occurs when rainfall intensity exceeds the abstracted capability of the catchment. It also occurs when the soil profile is saturated. Large amounts of surface runoff are referred to as floods. Rainfall varies in space and time. For modeling purposes, rainfall can be assumed to vary as follows. A. Constant in time and space, applicable to small catchments, as with the rational method. B. Constant in space but varying in time, applicable to mid-sized catchments, as with the unit hydrograph. C. Varying in both space and time, applicable to large catchments, as with reservoir and channel routing. The larger the catchment, the more likely that it is gauged. The probabilistic approach is suitable for large catchments, but also for mid-sized catchments. The parametric approach is suitable for mid-sized catchments, as with the USGS state equations. The unit hydrograph, a conceptual method, is particularly applicable to mid-sized catchments. Routing can be used for all size catchments, but it is required for large catchments, due primarily to the spatial variability of rainfall. In flood hydrology, the choice of method is a function of catchment scale. Hydrologic methods vary from country to country. Some conceptual U.S. methods, such as the NRCS runoff curve number, are used throughout the world.